From this lecture, you will learn two things. One, what is atomic inversion? Especially in pyramidal molecules. Second one, under which circumstances an atom can invert, or you can say under which circumstances an atom can have stereo center. So from this lecture you can get answer for these two questions. First one, before going to question 1, I have to talk about chirality of carbon atoms. I want to just recall it. Chirality of carbon center. Chirality of carbon. We know that if a carbon was surrounded by 4 different substituents, then this carbon will be called as chiral carbon and their mirror image. And the mirror image is non-superimposable. So, these compounds have 2 different configurations and the relationship between these 2 compounds are called enantiomers. In case, if these 2 compounds exist as 1:1 mixture, which are non-separable, then this compound mixture will be called as optically inactive, and that is called as racemic mixture. It is very well known in literature. Now the question is, and the people have separated these 2 compounds, and the 2 have 2 different, some cases 2 have 2 different properties, and as well as the optical activity was retained because of it's possible to separate them. When you substitute carbon hydrogen with nitrogen center. For example, an amine, nitrogen with 3 different substances, 3 different substituents. Then, is this compound optically active? First question, when you substitute carbon hydrogen with nitrogen, either this compound is optically active or not. Second one, why such compound? For example, if it is not, why these compounds are optically inactive? That we are going to see now. Just take an example of, because actually in most of the cases nitrogen with 3 different substituents are optically inactive. Why this optically inactive means the separation of the 2 configuration. The separation of the enantiomers are impossible. It's not possible to separate them. So always exist as 1:1 ratio. So that will be in the form of racemic mixture. So the compounds are optically inactive. In this case, the separation is the main problem. Why these compounds? We are able to separate the two different carbon having chiral center, but why not with the nitrogen substituents? Because the problem here is the term, now the new term inversion is coming, because this nitrogen center can invert easily. When it inverted in room temperature itself, if it is inverting from one form to another form, then the chirality will be, it will lose their stereo center. Like cyclohexane. Cyclohexane in solution, cyclohexane at room temperature, it can go to one form of the chair form to another form of chair form, maybe sometimes via board form. That is happening in room temperature. Similarly, in case of nitrogen substituents, nitrogen with 3 different substituents, even though it has lone pair electron, the compound will be optically inactive. That we can understand from the simplest example of ammonia. We can take a molecule of ammonia. If you understand this one ammonia, then it's very easy to understand amine also. So ammonia molecule, what it will do? It will go to invert. It will invert it into one form to another form. It can happen at a room temperature. How it's happening? It's changing the position of one of the form to another form by the intermediate of the sp2 nitrogen center. Because of the presence of nitrogen, the mass of nitrogen is higher in compared with the hydrogen atom. So to maintain the center of gravity, the nitrogen having lone pair electron is diffusing through the nucleus of nitrogen atom. It is moving from one side to another side through sp2 hybridizing state. At the same time, hydrogen is simultaneously moving forth and back. It's going front and back. It's moving forth and back. So what happened? It will invert their configuration because of inversion happened. So it can also be explained by energy level diagram. So if you can see the energy level diagram, from the energy level diagram, here x-axis we have the bond angle, y-axis energy. So the lowest minima is due to two different forms, and the highest one is due to planar transition state. That is an intermediate. It is A. This one is A prime, and this one is B. So the lowest two minima is due to A and A prime, and the highest one, the bump, that is due to B. So the energy difference between these two is 24.5 kilojoule per mole. So one of the form to go to another form, one of the configuration has to go to another form. That means it's like the ammonia that is turned out. The hydrogen is moving back, forth to back, moving simultaneously. All the hydrogen atoms moving forth and back simultaneously mutual. It's a kind of mutual motion. It's occurring. To occur from A to A prime, it has to cross the barrier that needs the energy of 24.5 kilojoule per mole. So it's occurring. This process is occurring. It's crossing the barrier via through the mechanism of quantum mechanical tunneling. Quantum mechanical tunneling. So through quantum mechanical tunneling, one of the form is reconverted to another form. In case if the quantum mechanical tunneling has to occur, it can occur only, this mechanism can occur only if the strain energy is less. The strain energy is less, then in that case quantum mechanical tunneling can happen. And also it can happen only with the light atoms, not with heavy atoms, because the two conditions need to be satisfied to occur quantum mechanical tunneling. One is the atom, the central atom should be lighter. Second one is the strain energy, not strain energy, inversion energy, the barrier inversion. This will be called as inversion barrier. So the inversion barrier energy should be minimum as much as possible. Only then quantum mechanical tunneling can happen. The lone pair electron can diffuse from one side to another side. At the same time, hydrogen atom can move from the back side to front side. So it can occur via the transition state of planar transition state. We know that the bond angle here is around 6.8 degree. And in case here the bond angle is going to 120 degree, again is coming back to 106.8 degree. So this inversion barrier can be changed with the type of substituents present in the nitrogen center. If the substituents, depending upon the substituents, inversion barrier energy will be changed. So the only thing is, because of the ammonia molecule can undergo this type of inversion, it loses their stereo center. The same answer, the same reason can be applicable for if N you put R. If you put N with 3R group, then it can, if it undergoes inversion, then it can, the nitrogen center can lose their stereo center, not a stereo center. Why is not a stereo center? Because this molecule can undergo inversion. If the inversion happened, both the form will exist in a mixture of 1:1 ratio, that is called as a racemic mixture, that is optically inactive. So this nitrogen center cannot be a stereo center if you put even the 3 different substituents with the nitrogen center. Okay, now let me put various substituents and then we can compare their inversion barrier energy. First, let me take a derivative of NH2R. Next one is NHR2. The last one is NR3. If in case R is equal to NH2 group, R is equal to NH2, then inversion barrier is only 2.8 kilojoule per mole. In case if it is CN group, 5.6. In case if it is nitro group, then it have 11.4 kilojoule per mole of inversion barrier. Then methyl group 20.1. Last one, chlorine has very high inversion barrier. It is greater than 42 kilojoule per mole. Similarly, here R is equal to methyl, then it has 28.1 kilojoule per mole. But when you go to tri-substituted amine, R is equal to again methyl group, here it has 31.4. From this I want to tell only one thing. In case if a nitrogen was substituted with a functionality that can form a pi bond, then that has negligible inversion barrier. For example, you can take NR2 with the cyanide functionality. If I put CN group, the CN can form, if you put a resonance structure, this lone pair of electron can engage to form a pi bond with the carbon center. Then that has negligible inversion barrier. Similarly, if I replace the nitrogen with the electronegative substituents, such as for example NF3, this one has lower bond angle compared with ammonia that we know. For example, NF3, the bond angle is around I think 103 degree. Even though it's 103 degree, if I put the electronegative substituents on the nitrogen center, the inversion barrier energy will increase. For example, it has the inversion barrier energy of 250 kilojoule per mole. So now we understood two things. With the nitrogen substituents, if any of the functionality can form a pi bond, can enhance, can facilitate to form a pi bond that has negligible inversion barrier. If you put the nitrogen atom with any kind of electronegative substituents, that has very high inversion barrier. Okay. Then next one is now let me see the case under which circumstances nitrogen containing compounds have stereo center, or I can say another way, under which circumstances nitrogen containing compounds cannot invert. You have to stop the inversion. You have to stop the inversion means the very important thing you have to know. First, that is case 1. If you take an example of case 1, you have nitrogen with 3 different substituents. Nitrogen with 3 different substituents, it can easily undergo inversion. That's why this nitrogen center can't be called as stereo center. So how can you stop the inversion? You have to stop the inversion and then you have to make this nitrogen center as optically active. The nitrogen should be optically active, or you can call as stereo center means then you have to stop the inversion. How can you stop that one? So just because if there is a presence of lone pair of electron, only then what happens? You can move from one side to another side. If you stop that one, there is no lone pair of electron, then what will happen? Then that nitrogen center should be a stereo center. The best example is nitrogen with the 4 different substituents. This compound is chiral. Why is chiral compound? Because nitrogen does not have no lone pair of electron. No lone pair of electron. Because of the absence of lone pair of electron, so what happened? There will be no possibility of inversion. So this nitrogen center has a stereo center, so that it has the property of chirality. So this compound is optically active compound. It's very well known example. And another one is case 2. Case 2. So if the nitrogen is in nitrogen having 3 different substituents having the geometry of pyramidal. So pyramidal having the hybridization sp3 is going from sp3 to sp2. So you have to stop the mechanism of sp3 to should not move to sp2. If you stop to go to if you stop to move to sp2, then what happened? Under that case, again what happened? Nitrogen can attain chirality. That can be possible by giving a strain to the ring. Strain to the ring. You have a molecule of acetylene. For example, if you put here one methyl substituents, then what happened? These two carbon have two different type of substituents present with the nitrogen atoms. Acetylene. So now you have two different type of molecules, acetylene and acetylene. In both the cases, nitrogen has strain. Strain in nitrogen center. Why these two nitrogen has strain? Because it each has the bond angle of very less degree. It has 60 degree. In this case, the bond angle is 90 degree. So, what happened? Even though it has the geometry of pyramidal, the bond angle is very less. So, it's not 107 compared with ammonia or anything tri-substituted nitrogen derivatives. It's less than that. So, what happened? This nitrogen center has strain in a ring. Ring strain is available. So, what happened? This nitrogen can't go to sp3 to sp2 state because it needs to go to 90 to 120 degree. It needs more strain, it needs more inversion barrier. It has to cross so much of inversion barrier. So what happened? Due to that, what happened? This molecule cannot reinvert. Inverted cannot inverted. So these molecules can be easily separable to make chiral, to get chiral compounds of nitrogen containing molecules. Then I can give another example also. Just to take an example of pyrrolidine. Pyrrolidine. Then next one is piperidine. Both the case actually what happened? Nitrogen atom in a cyclic system, but here the bond angle is, it has the geometry of pyramidal and it does not have any kind of strain. So this molecule does not have any strain in this molecule. So these two molecules can undergo inversion. These two molecules can undergo inversion. So it's impossible to separate. It's impossible to separate their racemic mixture. Racemic mixture of pyrrolidine as well as racemic mixture of piperidine. These two can't be separated out. So these two molecules does not have stereo center. So these molecules does not have nitrogen stereo center. Okay, I can give some more examples also for just to understand some more about this nitrogen inversion. You can see a molecule with bicyclic system. This molecule will be called as twin nucleodyne. So if you take this molecule, you can see that again this nitrogen center also in the pyramidal geometry. It does not have any ring strain, but nitrogen center is locked. Nitrogen center is locked. Because of the nitrogen center is locked, it is a kind of bicyclic system. Bicyclic system. So the nitrogen center is here, it is locked. So that bond angle can't go from around 107 to 120 degree. So what happened? It can't reach the transition state of 120 degree. So what happened? Again, no inversion. So this nitrogen center can be a stereo center. Next, I have another one similar type of examples. You can see carbon with two phenyl group and one nitrogen. Again, this is locked. Okay, so again the answer will be same here. So what happened? This nitrogen atom is locked in the form of a three-membered ring. So it can't attain the transition state of 120 degree. So what happened? It has very high inversion barrier. High inversion barrier. Because of high inversion barrier, I think around inversion barrier energy is approximately 250 kilojoule per mole. So what happened? If it has very high inversion energy barrier, this molecule, what happened? Cannot undergo inversion. So this can be a stereo center. Stereo center. Okay. So I have given some examples under the molecules under the nitrogen center can be in the form of ring, in the form of strain as well as no strain, and the nitrogen center is locked. All the things I have discussed under case 3. Okay. So finally, now let me go to, we can compare with other kind of pyramidal molecules. With the other kind of pyramidal molecules with the same row as well as just below of the periods. What will happen? The inversion barrier energy. Just to take an example of, I have already discussed about NR3 type system. We already discussed NR3 type system. It has an isoelectronic Cr3 minus, and it has again isoelectronic OR3 plus. It also has one unpaired electron. In all cases has one unpaired electron. All of them have pyramidal geometry. When you compare these molecules with their family members, for example, if the oxygen with the sulfur, what will happen? Nitrogen with the phosphorus, what will happen? Carbon with silicon, what will happen? I already said that one inversion barrier energy will increase when you go down from the first row to second row. So what happened? Inversion barrier energy increased means then what happened? That process of inversion, either it may be very slow or inversion will not occur. If the inversion does not occur, means that the phosphorus containing chiral compounds are easily separable. You can get back the optically active phosphorus or sulfur containing chiral compounds. So if you compare this one, this Cr3 minus has low energy barrier compared with the nitrogen substituted. Again, it has low energy barrier compared with the O oxygen substituted. Then I already said that one compared with this one, silicon has high energy barrier compared with oxygen, and which has a low energy barrier compared with the phosphorus, then sulfur. Then, okay. So when you come down, the inversion energy barrier will be increased. But in case if you compare this one, this is almost isoelectronic. This 3 is almost isoelectronic species, but even though it has lower bond angle compared with almost all of them have approximately the bond angle, because all of them have pyramidal geometry. So the bond angle will be very closer to 107 degree. Maybe this is exceptional. Even though what happened, the inversion barrier will depend upon the electron pair. The lone pair of electron has to diffuse through the nucleus of the central atom. It has to occur because the oxygen having positive charge. That's why what happened. This one has higher inversion barrier than remaining two. That may be, I think, best answer I feel. So if you compare this one, I think when you come down, the inversion barrier definitely will be increased. When you go to phosphorus to arsenic, of course phosphorus has low inversion barrier energy compared with the arsenic one. Okay. Then I can go to bent molecules. Bent molecules. So I have already discussed about pyramidal inversion, a molecule having the pyramidal geometry, pyramidal shape, then how it undergoes inversion, when it can undergo, under which circumstances it can undergo inversion, under which circumstances it cannot undergo inversion, that we have discussed before. Now let me take an example of bent molecules or angular molecules. This example we have water molecules. We know that water has two bonded pair of electrons and two unshared pair of electrons. So this molecule has to undergo inversion. Then it has to cross a linear transition state. Linear transition state. Then it has to, it can undergo inversion. This one, this process, like that, has to, the inversion barrier for water molecule is, inversion barrier is approximately 111 kilojoule per mole. 111 kilojoule per mole. So the water molecule has to undergo like that of inversion. Then, for example, if you put two, instead of hydrogen atom, if you put two different OR substituents, it can easily undergo inversion. So even though there is a presence of two different OR substituents, it has the ability to undergo inversion. So what happened? This oxygen center cannot be a stereo center. If you replace oxygen by sulfur, for example, hydrogen sulfide, do you think it has a low inversion barrier or higher? Of course, just the last 5 minutes before I said that one, when you come down to the same period, the inversion barrier will increase. So hydrogen sulfide has high inversion barrier. Inversion barrier is around 151 kilojoule per mole. So in room temperature, if it got this much energy means, then water molecule can, even though the instead of water with two different substituents, can undergo inversion to lose their stereo center. Okay, so then I think I can move to the last one. I just want to talk about tetrahedral molecules also. Tetrahedral molecules. Either is it possible to occur tetrahedral inversion or not. Tetrahedral inversion. So we have very well known example of a molecule of methane. Methane molecule has very good example for tetrahedral molecule. So this molecule has to undergo inversion, then it has to cross a transition state of planar transition state, then it can go to It has to go by a planar transition state. So here the inversion barrier energy is inversion barrier energy for conversion of methane of tetrahedral shape to planar transition state needed approximately 800 kilojoule per mole. Very high inversion barrier. So mostly the tetrahedral molecules will never undergo inversion. So it exists as purely in the form of tetrahedral geometry. Inversion is completely stopped in this case. The inversion will never occur because why? It has to cross this much very high amount of barrier. So what happened? It will be in the that's why what happened in our organic chemistry, most of the carbon containing molecules retaining their optical activity, or it has a stereo center. The reason was it does not undergo inversion. Okay. So finally, I think I want to talk about the reference. Reference for this topic is just to refer the book, just to go and see the book of Inorganic Chemistry. Inorganic Chemistry. Author name Holman and please refer, please just read this book to understand more about a pyramidal inversion or tetrahedral inversion. So I hope you understand I hope you understand about what is atomic inversion, under which circumstances an atom can invert, or we can say it another way, under which circumstances an atom can attain stereo center. So I hope if you understand this lecture, it will be easy, you can easily understand why most of the nitrogen tri-substituted nitrogen molecules are, most of them are optically inactive. That questions can easily get answered from this lecture. Okay, thank you, bye.